The citric acid cycle is the penultimate event that leads up to electron transport chain. Here, we're going to harness the mitochondria and a cycle that neither destroys nor creates any of the intermediate steps, but takes advantage of these steps to harness the energy contained in a high-energy molecule, acetyl-CoA, and generate high-energy compounds that can be used for the electron transport chain. I want you to see this reaction as one thing. People talk about, oh, this is the intersection of all the metabolism. No. The citric acid cycle, the tricarboxylic acid cycle, which is why we're calling it the TCA up to this point, or the Krebs cycle, is a cycle. I want you to see it as you enter at the top, you go through all of the steps once, the wheel turns a full 360, and you start over again at the beginning. This concept is difficult because it is very rarely taught this way. What I want you to see is that the only thing the citric acid cycle does is takes acetyl-CoA, which does have a lot of energy in it, and it burns it to carbon dioxide. Along the way, some low energy molecules, like 3-NADs, NFAD, and a GDP, happen to use this cycle to get some energy. And therefore, the yield of the citric acid cycle, the reason why it's so important, is that it yields high energy compounds, 3-NADHs, 1-FADH2, and 1-GTP. And we don't discriminate, GTP is basically ATP. But I want you to see that there is a complete and total absence of other substrates. Acetyl-CoA goes to carbon dioxide and generates high energy compounds that are either themselves already ATP or are substrates for the electron transport chain to generate ATP. It means then that this is not the intersection of all of metabolism, as some will have you believe. It is instead a cycle that happens to have the substrate names of other metabolic reactions. You don't enter the citric acid cycle or exit the cycle. You go in as acetyl-CoA, you turn the wheel one time, 360, everything happens, and what comes out is carbon dioxide as well as some energy. These energy are going to go to electron transport chain where oxidative phosphorylation occurs. In the presence of oxygen, ATP is made. Cells have oxygen and glucose brought to them so that they can go through the citric acid cycle to then use that oxygen to make ATP. The cardiovascular and pulmonary system bring oxygen from the environment to the cells and return to expel carbon dioxide from those cells. This plus electron transport chain is the reason why we have this system. It generates a ton of ATP and why our bodies are designed to take oxygen to the tissues and remove waste product CO2. Before we get to the cycle itself, and yes, you do have to memorize the substrates of the cycle, some general rules for the enzymes that matter. A dehydrogenase is anything that gives an H to an NAD. And if that is met, they're well named. Whatever gave the H, whatever the substrate was earlier, whatever gave the H to NAD is the name of the enzyme, substrate dehydrogenase. Now, if medicine were that easy and the citric acid cycle this important, it would never be tested. Of course, there are exceptions. So anything that involves succinate, either the input to succinate or the output, shares something similar to the way you think it might be, but it's a little different. A dehydrogenase gives H to NAD, succinate's a little different. Let's approach the cycle. Pyruvate came from glycolysis. Pyruvate dehydrogenase made acetyl-CoA. The beginning of the cycle is to take oxaloacetate, add it to acetyl-CoA, and make citrate. Citrate becomes isocitrate. Isocitrate becomes alpha-ketoglutarate. Alpha-ketoglutarate becomes succinyl-CoA. That sounds like that succinate guy. And yep, here he is. Succinate. Succinate becomes fumarate. Fumarate becomes malate. Malate regenerates oxaloacetate. This is what I meant by it, the wheel turns once. You put in the acetyl-CoA, matches with the oxaloacetate, and the whole thing goes back until oxaloacetate is regenerated for the next acetyl-CoA to run the cycle. Steps that are the classic dehydrogenase occur after isocitrate, alpha-ketoglutarate, and malate. Because they are dehydrogenases, they take a low energy compound, NAD, and form a high energy compound, NADH. That's true after isocitrate. It's true after alpha-ketoglutarate. And it's true after malate, NAD, 2, NADH. Because these take a hydrogen and add it to NAD, they are called dehydrogenases. Because they do what they're supposed to and don't involve succinate, they're the substrate name that gave the hydrogen ion dehydrogenase. The first is isocitrate dehydrogenase. The next is alpha-ketoglutarate dehydrogenase. The next is malate dehydrogenase. Pretty easy, okay? Succinate. What's wrong with that succinate guy? Well, he also has a dehydrogenase, and it's named appropriately. Named appropriately, but is a little weird. What does that mean? Well, this is where the FAD becomes FADH2. It's a little different because it's not NAD, it's FAD. And the input to succinate comes from succinyl-CoA. It looks like something's being built, like there's a synthetase. Succinate's a little different. It looks like by the arrow that's pointing to succinate, this would be a succinate synthetase. But it's named backwards. Named for another reaction that happens to involve these two substrates. So this is succinyl-CoA synthetase. I saved it for the end because it is the most important, not because it's rate limiting, but because it is the only other substrate level phosphorylation that we have other than in glycolysis, where a GDP is phosphorylated to GTP. That went a lot faster than expected. All you have to know is the substrates along the way, and this isn't so bad. As long as you remember which ones are the dehydrogenase steps, and that succinate's a little different. The big part about this is what the energy count is. So far from glycolysis, we generated a net of plus 2 ATPs. We had to put 2 in, we got 4 out, so net of 2. And 2 NADHs. Pyruvate dehydrogenase gave us 2 NADHs per glucose molecule. Here we see that acetyl-CoA gives us 3 NADH, 1 FADH2, 1 GTP per acetyl-CoA. Well, there are 2 pyruvates, 2 acetyl-CoAs for every 1 glucose. So the energy that comes out of this system is multiplied by 2 if we're getting the glucose per glucose count. So the citric acid cycle generates 2 GTPs, which count as ATPs, 2 FADH2s, and 6 NADHs, for a total count, net, 4 ATPs, 10 NADHs, 2 FADH2s per glucose. Now, this happens in the mitochondria. Electron transport chain happens in the mitochondria. These things go to electron transport chain and turn into ATP. There are true numbers that are somewhere in the half range because there's a trade-off between getting cytoplasmic stuff into the mitochondria, blah, 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 blah. Keep it simple. When asked about generation of ATP numbers, use NADH gives you 3 and FADH2 gives you 2. ATPs are already made in substrate level phosphorylation doing what they do, so they don't go to electron transport chain. They're supposed to come from it. What this means is that we've got 4 ATPs plus 30 ATPs from NADH and another 4 ATPs from FADH2 for a total of 38 ATPs per glucose net. Remember that if they ask you how many are made total, it's 40, but we spend 2 in glycolysis, so the net is 38. Also recognize that that was a hell of a lot of energy. A hell of a lot of those 38 ATPs came straight out of the citric acid cycle, temporally and regionally located in the right position to burn energy, high energy compound acetyl-CoA, to get energy as intermediates to build ATP. You'd imagine that something this important then, with this much energy production, would have some regulation. Indeed it does. Isocitrate dehydrogenase is the rate limiting step. And the cool thing about isocitrate dehydrogenase is that it is exactly like pyruvate dehydrogenase. Thiamine, lipoic acid, pantothenic acid, riboflavin, niacin required for it to work. Limited by substrate level regulation, inhibited by the things that it makes. And because the whole point of this process is to get to high energy compounds for electron transport chain to make ATP, high energy states are going to inhibit this enzyme. Why is it that enzyme that matters? Because of the liver. Nothing can leave the cycle, but there are substrates that do share the name of substrates in this cycle in other metabolic pathways. Because other people commonly teach them to you this way, I'm going to do the same, throw them in here, knowing that it is only in a different pathway that they arise. Citrate can go onto the cytoplasm to become fatty acids and fatty acid synthesis. Malate is the shuttle by which pyruvate turned into oxaloacetate through the process of malate leaves to go for gluconeogenesis. People will teach you malate leaves to go do gluconeogenesis. But put the acetyl-CoA in, turns the wheel once. That malate that acetyl-CoA induced or used in the cycle does not go on to gluconeogenesis. It is a malate from another metabolic pathway. And succinyl-CoA is a high energy compound which can be used for heme synthesis, and odd chain fatty acids can be broken down and turned into glucose because they go through succinyl-CoA, which eventually through reversible reactions end up as malate, which can go to the cytoplasm. But these are rare, and that's not what I want you to learn. Fatty acids are built from acetyl-CoA. Fatty acid catabolism gives you acetyl-CoA. Fatty acids cannot be turned into glucose because they start at the top of the wheel. Fatty acid catabolism ends up with acetyl-CoA. The wheel turns at 360, starts over oxaloacetate, ready for the next acetyl-CoA, except in the liver. If the liver has a high energy state, lots of FADH2s, lots of NADHs, lots of ATP, isocitrate dehydrogenase will be inhibited. And if there's complete inhibition of isocitrate dehydrogenase, this step, the one that takes citrate to isocitrate, will be arrested as isocitrate accumulates. What happens to that citrate? Well, it does only one other thing, and that's shunted off to the cytoplasm for fatty acid synthesis. We just said 27 times that acetyl-CoA in the top spins the wheel 360, it never enters and never leaves, except in the liver. In the liver, oxaloacetate and acetyl-CoA can form citrate, and because there's nowhere else to go in this cycle, excess goes off to the cytoplasm through the citrate shuttle to become fatty acids. What do you really need to know from this? ATP production. The fact that most of the high energy compounds for electron transport chain come out of citric acid cycle. Citric acid cycle in all cells except the liver. Put acetyl-CoA in, spin the wheel, no entry and exit. The only difference is in the liver. When energy compounds accumulate, regional level regulation slows down the cycle such that citrate builds up and is shipped off to the cytoplasm. This isn't that hard if you remember all of the steps along the way and then mark which ones are dehydrogenase. And oh yes, succinate's a little different. Getting the names right. And then you're going to have to work through this a couple of times to make sure you know for certain where those high energy molecules come from. That is a citric acid cycle.